transported and distributed in piping systems every single day. They can include solvents and chemicals, oil and gas, or steam for energy transmission. The fluids flowing through pipes often have completely different properties. Therefore, different principles for their measurement are required.
Yeah. So we'll talk about measuring fluid velocities and flow rates in pipes and in open channels today. Hence this, using Bernoulli.
Swiss mathematician and physicist Daniel Bernoulli discovered the direct relationship between the pressure and speed of a fluid flowing in a pipe. Italian physicist Giovanni Battista Venturi also performed experiments on flow, and in 1797 he built the first flow meter for closed pipes, known as the Venturi tube. Here is how this measurement method works. Differential pressure flow meters have an artificial restriction integrated into the measuring tube, illustrated here by the example of an orifice plate. Two holes are located in the pipe wall, one before and one after the orifice plate. Two separate tubes connect these holes to a differential pressure sensor with its two pressure chambers separated by a diaphragm. The tiniest pressure differences in the flowing fluid can be precisely measured. If the fluid is not flowing, the pressure before and after the orifice plate is essentially identical. As soon as the fluid starts to flow, its velocity around the orifice plate increases significantly because of the restriction in the cross-section. At the same time, due to the laws of fluid mechanics, the static pressure at this point decreases. Consequently, different values are detected in the pressure chambers of the sensor, a higher pressure before and a lower pressure after the orifice plate. This pressure difference is a direct measure for the flow velocity, and thus the mass and volume flow in the pipe. The higher the flow velocity and the resulting drop in pressure around the orifice plate, the greater the differential pressure measured. In numerous industrial applications, the orifice plate
Sorry, I don't know. What's the other guy?
nozzles are particularly suitable to higher flow velocity.
So yeah, so you can have a plate across it with a hole in it, an orifice in it, or you can have a more gradually varying flow to get better results for measurements. But I guess the key thing here is that you can measure, it's easiest to measure a pressure in a system rather than have a little impeller or an anemometer, which you measure wind speed with, these little cups, 3 cups that float around and go at a different speed based on airspeed. You measure pressure, no moving parts. Instead of measuring pressure with a gauge upstream and downstream, you have a differential pressure measurement, which measures just the difference in those pressures, which is what you need. And I suppose you do the same in a pitot tube, right? A pitot tube, all you need to know is the difference in pressures on the one where the flow is parallel to it and the one where it hits it head on, and that gives you the velocity of your plane, etc. So we'll talk about this for flow measurements today. And so in 2 particular modes. I've talked about an anemometer for hurricanes, of which we have one raging in the Gulf right now, Helene. And if we want to measure flow rates in streams, if you are in the backwoods and you want to measure the discharge rate in some small ditch that's flowing, then what you typically do, you put a board across it. Maybe the board has a cutout in it, and you measure the height to which the water flows across that board, and you can relate the height of the flow in the board to the behavior. See if I can get that back. This is back, yeah. You can relate that to the flow rate. And so that's what we'll concentrate on today. So that's our plan. So midterms. They were decent scores. I know some of you don't think they were. 68, 80, and 72. Those are par for the course. They're probably higher than normal, if that gives you some hope. Some people were obviously very happy with it, aced it completely. Some people stumbled on one test, one of the days. I didn't get any thank you emails, so thank you, but I did get 3 ones giving long statements on, slipped up on this and it carried through, and carry on questions. And yeah, there are carry on questions. Not so much. In the Wednesday exam, maybe 50 points were carry ons, and the other ones later on were independent. On the Friday one was the other. I had one question about that. Again, 50 points. The end points were completely divorced from the earlier questions. So I think it's not possible to have not follow-on questions unless we have questions like the first test, which was like your first assignment, homework 1. Calculate this in MLT, calculate this in MLT, completely unrelated. That's not really testing, and no, you're better than that. So that won't be a typical form. In terms of the good thing about the emails I got, they weren't complaining, they're just pointing out some things. And they all were saying that, well, I need to take care of this, and so I think that's right. Certainly the tests aren't going to change. You know my reasons for having these binary answers with plus or minus 10% based on what you have to do ultimately when you're an engineer. In preparing for these, if you're not preparing from the previous tests, you're not doing yourself a good service. If you didn't realize that both Wednesday and Friday were retreads of previous questions, then you're not preparing, I think, the best way, I would say. The Wednesday question was actually a retread of an almost identical question, the venometer question from 2013, which was a partial credit open calculation question. Of course, the question is different. You end up with the same place, but you don't get told you have to calculate this, and then you calculate this, and then you calculate this. It just said calculate the average density for a mixture of X alcohol and 1 minus X water, calculate the average surface tension, calculate the height rise. You've got the height rise, use this figure. If you change the mix 70-30 to 30-70, what you get. And so I did have the scores, and the scores were lower for the partially graded one. So you might think that you'd be better off with partial credit, but perhaps I think you're not. So that's my statement on that. And yeah, so I don't know what else to say. So shouldn't be upset with yourself if you stumble and on one question. Perfectly easy to make it up. 70% of the grade is on tests. 10% extra is another 7%. So each one of these tests was 6.66%. So you can throw away one test for the extra credit portion and not worry too much about it. I did say in the email that scores generally get a bit better because they become more formulaic, more recipe-like as you go down the road. And so, and I think also perhaps you know what to expect more, even though you've been told what to expect before. Perhaps you don't believe it coming in. So some people won't want anything to change at all. Some people want to maybe perform better, but that's fine. But I don't see any crises here. It's pretty much par for the course. So that's my rah speech, if you want it. Questions, comments?
Is the exam extra credit, is that already applied?
Yeah, it's out of 110 points. So if you've got 110 points, you have 110% for that. So it's automatically done in Canvas. I don't know if you see it in Canvas. It's your scores, which get they're quoted as a point score out of 110. Canvas calculates them as a percentage. So I multiply the scores in the complete tally by 1.1, which is the 10%. I know, too complicated. You want to shoot yourself, right? That's so complicated. But yeah, that's it. So. We split the tests over 3 days. I think it's good, so you can recalibrate if you come into the first one and it isn't quite what you want, then you have a chance to catch up. Yeah, I don't see any crises. So, comments? Other comments? Sure. Yeah, fine. If you want to vent, I'm around today. Out, as I mentioned, out on Monday. So, asynchronous on Monday, as you'll find out from your email that comes in at midnight tonight, when I don't really send it, but it's sent at midnight. Okay? Great. Good having you here. We're a bit light today, maybe. Who knows? Oh, it made me feel bad. All right. Next test, someone asked me, so the great thing about the emails I got, okay, didn't work out so well. Here's the reason I think you should change it. Perhaps you're not going to change it. No, we're not. I need to get it together for the next test. What's going to be on the next test was one question. So the next one is chapters 3 to 7 inclusive. And I think the questions, will be a video, so I'm not saying anything I won't say, are going to be 3, 5, and 7 in terms of the 3 questions. 3 is forces on structures, moments around gates that are opening, etc. 5 is what we've talked about this week. Typically, I'll only put things on tests that we've physically talked about in class, if you don't realize that. And 7 is something we haven't talked about, but it's conservation of momentum, which is same as there was in one of the videos, a 747 on San Francisco International, right? Blowing a truck off the side. Yeah, same principle as that. You kill Bernoulli, a more sophisticated way of doing it than just doing it with Bernoulli, which is how we did that. So that's good. And it's not for a few weeks. Obviously, it's after week 7, so it's probably it's the same as it's on the syllabus. So anyway, necessary evil, as I mentioned. So just deal with it. Want to chat with me? I'm around today. I'm around probably Tuesday afternoon and onwards next week. Okay. All right. Last Bernoulli parts, not last fluid mechanics. We've been spending most of our time talking about along a streamline. By far the most important one that we'll talk about. This is much more exotic. You can take that from whatever you want to interpret that to mean. We've been talking about Bernoulli. We haven't talked about these things like pump heads and losses in pipes. So these have all been zeros. We'll talk about those in due course. Pipe flow is all about this. The essence of losses is what makes pipe flow. The essence of losses in porous media flows is what makes porous media flows important. So we've dealt only with these components. I guess in terms of summarizing maybe what we've done, probably talk about a couple of things. This is summarizing what we've already talked about. And we could have flow out of a container. And we've talked about free jets in different ways. You know that we just write the equation between points 1 and some other location. We know that if this is a free jet, then this is a velocity which is equal to square root 2gh as a standard result. It comes from Bernoulli. It comes from our assumptions that big tank assumption, V1 equals 0, so that term drops out here. This term is not 0, that's kind of the object of what we want to understand. But we know this is atmospheric pressure, this is atmospheric pressure. The pressures drop out, and so you're left with a velocity term on one side and an elevation term on the other side, and this is what comes out of it. We know that in free fall, this is exactly the expression of if you took a pen at point number 1 and dropped it, then by the time you get to point number 2, the acceleration due to gravity would be exactly what this pen would be doing. And so that's because we're not doing anything in this other than solving F equals ma. The acceleration terms is this, v squared over 2g, and the force terms are this and this, adding the force, as you could surmise. We could turn this on its side. Now I've done this. And instead of having it come out of the bottom, we could have it come out of here. And if we do that, then we can also do the same thing. It turns out that certainly in terms of Bernoulli, we're talking about streamline velocities, v2, which is also a streamline velocity. That's what we get. We know that where it comes out of here, this is v2 still equals square root 2gh, where h now would be just this, of course. We've closed this off, right? So this would be 2gh, and we'd get that just by using Bernoulli between points 1 and the new point number 2. We know that this has a component which we talked about last time, which is a velocity in the x direction, which is v2 cosine theta, v2 sine theta. And if we want to know something about how high this gets, we can write between this point and this point. We know that this velocity here is going to be v3, but we also know that v3 has to be equal to v2 cosine theta. Has to be the same as this, right? I'm moving across the room. Newton's law says that if no force acts on me, I keep on going at the same velocity. Can't decelerate. And so we know what this velocity is here. We know what this velocity is here. We know what this pressure is 0. We know that this elevation is 0. And we don't know what this elevation is. So we have one term to solve for. We get that elevation. And if we think of the fact that, as we talked about last time, if we're squirting directly upwards, then this will go exactly to the height of the level of the water. At this level, the streamline velocity will be 0. It'll be decelerating as it goes up. It'll be using up all of its potential energy as it goes up here. It'll stop here because it has no potential energy, z, and the velocity is equal to 0, and it'll start falling down again. So that's the same that's happening here. Pens up at lowercase h, okay? This h is not the same. This is h3. This is h1. So it starts off at h3, and it drops. And so the time it takes to drop this height z, you can calculate from your statics equations. And if you know how long it takes to get down, you know how long it takes to get to this point here. If you know this velocity, then you have velocity equals length over time. So length is equal to velocity times time. You know velocity, you know the time to go half the length, you've got a length. You want to know the full length? 2 times. So that's it. So we did that. We also did something to look at the case. We didn't talk about it in great detail, but we alluded to the fact, and we did this very quickly. We said, what happens if something is coming out of here at these 2 points, 1 and 2. What happens if this is a cross-sectional area, which is an area rather than being infinite area? And what happens if this, as we assumed before, is actually quite small? If that's the case, then we can't necessarily get away. If this is actually a small enough area that this is flowing at some velocity v1, then we need to account for that. And so if we account for that, then the second thing that we utilized is the continuity equation. And I mention it because we're going to use that today for these Venturi tubes, because to link the velocity upstream and downstream of this orifice, we're going to use continuity. So in this, we'd use the fact that the velocity 1 times A1 is equal to the velocity 2 times A2. We would use this to calculate that V1, therefore, is equal to V2 A2 over A1. And then when we use Bernoulli, we throw this in here, so that now when we use Bernoulli, we've got something in terms of V2 and 2 areas, which we know, and something in terms of V2 and no areas that we don't need to know. And so we've immediately taken care of the fact that we probably, when we solve this equation, we have 2 unknowns in Bernoulli, and we get rid of it. And so we didn't spend much time on it. but this is the result that comes out of it. We get an expression like this. It's still steady state because we're flowing fluid in here, so this level stays the same. It doesn't fall down. And so we're saying, what is the flow rate that we have to replenish this velocity? If Q wasn't going in, then this water level would slowly go down with time, right? Because of the velocity that it's dropping with. So we have to do that to keep it steady state. And if we do that to constrain it, we end up with this expression here. And so this is just equal to V2 is equal to 2GH square root times 1 over a term. And this term, if D is we've done it in diameters here instead of areas, it ends up being diameters to the fourth. If it was areas, it would be the ratio of the areas to the square, because area is proportional to diameter squared. Doesn't matter. But if D goes to infinity, infinite tank size, then this goes to 0. This is 1 minus 0, and this just reduces to this. If it's not that case, then we have to account for that, and we accommodate it for being able to use continuity between upstream and downstream. So sometimes when we look at doing these calculations, things get mired. You know, in the weeds, it's not so plain. But this is what we've done. We've made sure that this area is now finite, so that this velocity is something. We kept it steady state by keeping it topped up by Q coming in, flow rate coming in, so we didn't violate our steady state. And so now I'm going to be very smart and do this. What we're going to talk about today, doesn't want to do this. Didn't want that. See if I can do this. Oh, genius. So, look familiar? It's Venturi flume, right? So we just looked at these examples from the company. Upstream flow, downstream flow. I guess if it was to open up again like this, it would do this, right? This would be an extreme version of a Venturi flume that we just looked at. Now the jet coming out of the bottom of this tank is not an orifice into air, but it's a tube that connects them, and it's exactly a Venturi flume. And so perhaps we wouldn't be surprised if the equation that we get that gives us, here we talked about the free parameter being a value of the head between upstream and downstream. Pretty much when we look at this, that's not a very good one if I draw it through this. If we look at a point upstream in the tube and downstream, this is going to be z equals constant. And so probably at these locations, we're going to want to know what P1 is and what P2 is. And so we can do the same as this. We can write Bernoulli on the streamline here. We can write Bernoulli on the streamline here. Elevations are going to drop out. We're going to be left with pressures. We'll have a pressure upstream and downstream that if we know the differential between it, the membrane differential transducer you saw in that movie would be P1 minus P2. That's what it's measuring. And we want some way to link V1 and V2, and we can do that through this expression here. So that's the big picture. So we'll end up with some standard results that will look like this. So this is the idea. We'll maybe come back to this. This is only making a point that if you constrict it too much, then you know that the velocity increases. If the velocity increases, then it increases at the expense of the pressure. If the pressure drops too much, you can actually boil the water in here. You can make it bubble. It'll cavitate. That won't give you good readings, so you need to design this so that the transition is quite smooth and back out again. We'll come back to that. So these Venturi tubes come in different varieties. This one is better than this one. It could be just a plate with an orifice in it. It could be an angled orifice plate, or it could just be a contraction in the pipe. The smoother the change, the less chance that you have all these vortices developing, as the question was last time. Why do these vortices develop? And I guess a better answer, rather than tornadoes, is that this is really happy to go along here, F equals ma, at its own velocity. It has its own momentum. So it's happy to go on the straight line. But because it's going on here, a space is opening up from continuity behind it, and it gets sucked in. So as it gets sucked in, it's turned in a vortex, and it forms this little eddy behind it. So better than a tornado explanation. If you want to get rid of that, then you have it much more aerodynamic or fluid dynamic, and you have the transition much more gradual. So how do we get an expression for this? Well, there's standard results. We take a line down the middle, which is a streamline. We can write the pressure upstream at point 1. We can write it in the orifice itself at point 2. We know the upstream and downstream elevations are the same. We know that we'll have Bernoulli's equation, which has, instead of 6 components, has 4 components because we got rid of 2 of them. We can link the velocities at points 1 and 2 through the areas which we know. And so now, instead of having 4 parameters, we have 3 because we've linked this to this. We have it only in terms of one of the velocities. And then if we realize that we want to measure the difference between P1 and P2, not the absolute magnitudes of those, but the differences, by having a pressure gauge in here that measures on the diaphragm. Remember, it was just a diaphragm here that was it's a little flexible diaphragm. It has a strain gauge on it, so that if the pressure here is higher than it is here, which it would be, then the membrane bends. You measure the bend in that membrane, and you calibrate it against upstream pressures and downstream pressures, and that gives you P1 minus P2. So if we apply Bernoulli to this, by substituting, we'd substitute V1 is equal to V2 A2 over A1. We'd put that in here. We'd play around with this. I know we did that because we're getting the fact that volumetric flow rate is equal to A2 times V2, right? This whole expression. So this expression here, this is just an area times a velocity. That's a volumetric flow rate. Length over time, length squared, length cubed per time. So this whole term here is just a velocity. And this is how it works out if you just solve Bernoulli. Standard result. You see here that this is in terms of the area squared. You saw that for the tank question, we had it in diameters to the power 4, because we know that area is proportional to d squared. So this is area squared. So I'm just trying to rationalize these things. And a standard result. So you know the cross-sectional area of flow. You know the pressures upstream and downstream from the gauge. You know those areas, and you know the density of the fluid, hopefully, and you get a volumetric flow rate. So no impellers or anything measuring flow rates that have moving parts, purely solid state measurements. If area 1, let's see, if area 2 is very small, I guess if area 2 goes to 0, then I guess this term becomes 0, and this just becomes 1 over the pressure drop between the two. That seems kind of strange. Oh yeah, no, it makes sense, right? Actually, it's the pressure drop times the area. And the reason for that is if area 2 becomes disappearingly small, it's like flowing fluid into a brick wall. And so it'd just be like the jet engines on SFO hitting the truck. This comes in at some velocity V1, it hits the truck, the pressure it builds up is equal to P2, nothing goes past it. So the pressure on this wall would be equal to P2. And it would be the same as just killing all the velocity. So I think that's what this means. So this is just, actually it's Euler's equation. Was that one of the questions on the test? No, I guess it was Reynolds' number on the test. EU is just the pressure divided by rho times V squared. I think you were asked what the dimensions of that were. So this is the velocity of the fluid that hits you in the chest. This is the pressure that is on your chest. And if it's water with a high density, it hits you harder. We can use this number to get the force that's applied. Okay? So that's Venturi flumes. I don't know, you've got lots of these examples. Let's do this example. So we'll do measurement in pipes, which we've just done. You could also do it by measuring, instead of using a differential transducer to measure the pressure here, upstream here, and downstream here. You could also use manometers to do that. This is a more complicated solution. They choose the solution here that's more complicated. But if you're given a question to do this, how would you solve it? You have a velocity upstream, you have a velocity downstream. You can write Bernoulli along that line between those 2 points, at points 1 and 2. You can look at what the conditions would be here. This is stagnating, so velocity 1 is equal to 0. It's hitting the pitot tube. The pressure is not equal to 0, so you don't know what this is. The pressure 2 is not equal to 0, so we want to know what this is. And the velocity 2 is probably not equal to 0 either. It has some velocity. And we know that if they're all on the center line, that the change in elevation between upstream and downstream is 0. So this term goes out, this term goes out, upstream velocity goes out. We're left with upstream pressure, downstream pressure, and this velocity. We have to figure out what that is. So we only know the differential pressure, so hopefully we can get the differential pressure and therefore solve for velocity. We can get the differential pressure because we have it intrinsically defined in this manometer tube. And so you just need to do that through these two expressions. It's not very useful to do that. If you want to get P1 minus P2, so if you rearrange Bernoulli, you get this. Trust me. So you want to get P1 minus P2. So let's write the manometer equation out in terms of that. P2, let's start at this point. We go up to this point here. So this is minus H plus L times unit weight of the flowing fluid, right? We go up from here, we go up L, we go up H, and we get to this point here. We come down, so we add H times the gauge fluid. Gets us to this point here. We skip across to here because we can, we're simply connected. And now we know the pressure here is the same as this, which is the same as the pressure here. And so we can go down here, so we can add L times unit weight. And that is equal to P1. We can subtract P2 off both sides. And so this is the expression we have. Some of these terms we get rid of. I guess we only have one term with the gauge fluid in it. We have this term here, which I think will cancel out with this because of the negative. And we have minus H gamma plus H gamma G equals P1 minus P2. And we can write this left-hand side much more readily as H times gamma G minus gamma. They do this, but they ultimately get the same expression. much better to do it this way. And so now we have an expression for P1 minus P2 instead of in terms of something we know. We know the density, unit weights of the fluids, and we know H. We can substitute this into our Bernoulli expression, and we end up solving it. So, big picture. So, write Bernoulli. We have too many unknowns, so we can use, actually basically using continuity to link these. Once we have Bernoulli, we have 3 unknowns in the equation. So we want to get velocity, so we want to be able to solve for these 2 unknowns. We don't know them individually, but we can get from this manometer their difference. It's a differential manometer, right? That's what it's called. It's just the same as a differential pressure transducer. Instead of measuring the pressure in this pressure transducer as 4,000 MPa and measuring the pressure in this other one as 3,999 MPa, and then hoping that the resolution of pressure transducers is a percentage of the full range. And so the reason for not wanting to use individual pressure transducers is you get a much more refined reading for a differential reading, because your range might only be the 1 MPa that's different, not the 10,000 MPa, which is the maximum scale on each of them. Okay? All words of wisdom. I know you're soaking it up on a Friday. So in pipes we talked about, and we've just done that example. Open channels is much the same. We use weirs or sluices. We can define them as undershots or overshots. The one we looked at in the video was an overshot. It's not unusual for you to go out as a beginning engineer and working in the field, get the flow in this ditch. You take a spade, a shovel, you put a plank across the ditch, and you measure how high the fluid flows across the plank. That's essentially what we're doing here for an overshot weir like this, which we'll get to in a sec. But the idea is the same as a free jet. We know if we draw Bernoulli between points 1 and point 2, pressure 1 equals 0. Pressure 2 equals 0. It's on the surface. Head, the height that we'll use in Bernoulli is equal to Z1 or Z2. And this may be V1, and this may be V2. Obviously, if this is really, really deep, and this is really, really shallow, then V1 goes to 0, compared then, I guess, V1 over V2 goes to 0 if V1 is very big or V1 is very small. But we don't need to make that assumption. We won't make that assumption here. So we write Bernoulli between upstream pressures, downstream elevations. The streamline that we take is on the top of this. We have the velocities upstream and downstream. We can use continuity to link them because we have these 2 velocities that we want to somehow link. They're not zeros, but we can link them through this. The cross-sectional area is going to be equal to the depth of flow multiplied by how wide our sluice is, which is what this is. And if we multiply velocity times area, we get volumetric flow rate. It's steady state, so the flow rate here going into our control volume has to be the same volumetric flow rate coming out, a requirement of Bernoulli. In other words, a snapshot of this now and in 10 minutes, this is the same velocity here, this is the same velocity and height here. And if we manipulate it, we get something not very different from what we had before. Volumetric flow rate is equal to an area, which is this term here, multiplied by a velocity, happens to be a velocity at location 2. Elevation difference between upstream and downstream, the ratios of the upstream and downstream flow areas. It's a length squared because they have the same width. B, this would be Z2B over Z1B. The B drops out. And if you just have the information about the upstream elevation and the downstream elevation, you have enough to calculate that. If Z1 is very big compared to Z2. Or alternatively, Z2 is very small. This term goes to 0, and you end up with this expression. This is just a free jet with the upstream velocity equals 0, right, as we did. So this is the free jet times an area. So again, Q is equal to V2, sorry, A2 times V2. Okay, so that's it. So standard results. The shape of these orifices might be different, so we might want to have a correction. I'm not sure what A is on this. No, A is the fact that the height of the sluice off the ground might be different from what this develops into because of a so-called vena contracta effect, that the flow contracts as it goes downstream. Let's not waste time on that, but if we know something about the geometry, we could have a correction that we could also apply to this if we wanted to. So in other words, we multiply this through by some correction, which should be non-dimensional because we know that this is units of meters cubed per time. This also is in meters cubed per time. So any correction has to be dimensionless. And this would typically be reducing the flow between 0 and 1. And here it is. An overshot weir is the same idea. Actually, it's much more intuitive to a free jet. You could probably think of drawing this system as this. Say if you had water level upstream, which was this, and you flow it over a step, which is this, what do you think it would do? It would go downstream, and it would go over the top like this. So I think if you wanted to, you could think of this as being kind of this, in which case the water would be traveling out of here at some rate which is controlled by, bang, which is controlled by the height of this flow relative to this. So this is just a free jet, right? It just looks a bit different. And the reason we know that is that when you flow across this sluice, it will separate. And it's the vorticity idea. It's happy as a clam going here at some velocity. Force equals ma. It has some velocity. F equals ma is equal to the same as F equals mv squared over 2. It's that term within the Bernoulli equation is the momentum term. And so it's happy as a clam, just keeping on going. Of course, gravity starts acting on it. So if it's fast, it will go a long way before gravity pulls it down. And therefore, it separates from the bottom. And so if you're sitting here, you'd be able to happily sit here and breathe air because that's what's there. So this is really just like a free jet coming out of here. A free jet would do this, top and bottom, right? And so it's not surprising that if we look at the velocity, it's controlled by something related to the height of this flow. And so if we do the height of this gate compared to the height of this, which is this term here, we would expect that the velocity coming out of it would be proportional to the free jet equation. This is velocity 1 times a correction, which we said because of the geometry is not quite right. If we wanted to get a volumetric flow rate, it would be V2 times the area, 2. The area is just the height of this times the length into the screen up here. And of course, the correction might be for the form of the flow. If it's a notched plate or if it's a rectangular plate, as we saw in the video, this correction factor would be including that. And we can write this. If we know that this area is composed of the height of the flow above the sluice, and this height also exists within the free jet equation, then this becomes height to the 3 over 2. Instead of height to the half, height to the 2 over 2 becomes height to the 3 over 2. Just a way of defining the equation. So those are kind of standard results. So, much easier. We didn't look at an anemometer. You know what an anemometer is, right? These little white cups. I don't know if it's white, but 3 cups that twirls. The air catches the open cup much more efficiently than when it goes around and the cup is closed. And so it drags it in one preferential direction. These are too difficult to do. Let's not do those. Let's talk about what this looks like. Physically, graphically, it might be useful to talk about these. We've talked about a pipe that's flowing. So if we think of a pipe, this second thing here is a pipe where we have flow from upstream to downstream. This is point number 1. This is point number 2. This is V2 out of the pipe. This is V1 into the pipe. If we think pictorially about Bernoulli, actually I'm going to draw this. The fact that Bernoulli is the sum of 3 quantities, upstream and downstream, then we can think of this as being Z1 and Z2, right? This is the elevation halfway through the pipe. This is a pipe, nothing else. So the flow is within here. This is V, which is the same as V1. We know that V1 A1 equals V2 A2. So if A1 and A2 are the same, then the velocity V1 and V2 have to be the same. And we know that the pressure in this is some magnitude. So I'm going to draw the pressure here as this and rationalize exactly what this is. So this is P1 over gamma. This is P2 over gamma. And I'm going to draw this line here. And this is going to be V1 squared over 2G. And this is going to be V2 squared over 2G. And I'm going to call this the energy grade line. GRADE line. And of course, as you know, Z1 plus P1 over gamma plus V1 squared over 2G equals Z2 plus P2 over gamma unit weight plus V2 squared over 2G. That's Bernoulli. This is pictorially what it says. Horizontal pipe, elevations have to be the same upstream and downstream. So these are equivalent to each other. Not zero, but equivalent. We know that from continuity, if the pipe cross-section is the same all the way along, then V2 and V1 have to be the same. So these two have to be identical to each other, not zero. And so these heights here that I didn't label have to be the same. And since Bernoulli from upstream to downstream in this energy grade line, this equals constant, and it equals the value of our energy grade line. You know, we could choose our datum anywhere, right? We could be there. The datum could actually be above us if we wanted it to be. And so by definition, if this has to be equal to constant, then the pressures upstream and downstream have to be the same, by definition. This is specific to Bernoulli because it's inviscid. There's no viscosity, so there's no energy losses in the system. So as you go from upstream to downstream, the energy downstream is exactly the same as the energy upstream. So it's not a real system. as we'll see as we go ahead. So this is the last time we'll deal with it. But it's a pretty good approximation of what goes on. So we call this the energy grade line. We call this line here the hydraulic grade line. Just out of convention. And the hydraulic grade line is just the sum of the elevation head and the pressure head, just by convention. So that's a useful way for us to think about this. For Bernoulli, in Viscid, the energy grade line is always horizontal. There's no loss in the system. And so that's what this is saying here. Hydraulic grade line, energy grade line. And so if we look at a system that's a bit different, then kind of a free jet, a big tank, flow coming out of it in a pipe that constricts twice, then we can do something with the energy grade line. We know this is always constant. We know that if we take this as our datum here, as z equals 0, then if the velocity in this big tank is equal to 0, then that would be P0, pressure 0, and velocity 0. So this would be the location of the energy grade line. We know that a streamline that comes through this, as it comes through and goes through the middle here, then what happens? This can no longer be 0 velocity. So we know that the velocity has to be finite. It's probably bigger than 0, just from what we think about it. So if this is finite, then this will pull down this magnitude here. So right at this point here, this is the elevation head, Z1. The pressure head is infinitesimally thin line, and the velocity head, V squared over 2g, is an infinitesimally thin line here. They're all converged. As you come here, they diverge. The velocity will widen out, finite, at the expense, and we'll lose elevation at the expense of both pressure and velocity. As it further constricts, then from V2A2 equals V1A1. So we know from this that V3, we know from this is that V3 is going to be equal to A3 over A2, V1, V2. We know that A3 is smaller than A2, so this has to be faster. So we know that we're going to gain velocity at the expense of pressure. These are on the same elevation, so Z won't change. But what's going to happen to pressure? Pressure is going to be reduced. How much is it going to reduce? If it's coming out here, then by definition the pressure at 3 has to be 0, atmospheric. And so we mean that we've completely shut down the pressure. Pressure is an infinitesimally thin line for the pressure head here, and it's completely dominated by the velocity head and the elevation head. And so that's it. So that's the best explanation I can provide for what we've talked about. And so you can use the same rationale. If you're in the lab and you want to use de-aired water, the quickest way to de-air water is to take a piece of Tygon tube, a hose pipe, fill it up with water, and then take the middle point of that up 10 feet, 30 feet, sorry. And if you do that and make water flow through it, then water will come out of this, it will go out of here. Because the pressure here has to be pressure 0, we know that if you pull the pipe up here, the elevation here is Z. The pressure head has to go down because the velocity head along this constant diameter pipe has to be the same all the way along it. So this will be a negative pressure, or less than atmospheric. If it's much less than atmospheric, it'll reach the cavitation pressure, the vapor pressure for water, and we know that's about 30 feet. So if the pipe goes up 30 feet, the pressure at the top of the pipe of the siphon will be at absolute 0, close, and it will cavitate. And it will pull the air out, and the air will gather in the headspace in the top of the pipe. That has been a good question on tests. Not this year, I don't think. But anyway. And the final curious thing, and you can show this for yourself. You can use the same rationale for this. Venturi flume is you constrict flow within a pipe, or you do it with a sluice. You could also do it by putting a bump in the bottom of an open channel. And you might think intuitively as you do that, that what should happen is it should go up like this and down. But you can show, I don't know why my phone is ringing in my pocket now, but it is. You can show that counterintuitively it has to go down. And it has to go down because if it would do this, the energy grade line, which would be a constant line, doesn't have a way to be able to accommodate a rise in the elevation of this point and also have a velocity that fits with that. You can show that to yourself if you want. So that's the very last thing that we talk about, I think. Apparently not. So this last part just talks about our assumptions. Remember Bernoulli, in viscid, viscosity is equal to 0, steady state. You take a picture, it's the same. So if your bicycle is moving into the wind, you have to attach yourself to the bicycle. No vortices, incompressible. Actually, we do use it for air all the time, which is compressible fluid, and it actually works reasonably well. But it doesn't work when you get to Mach 1, above the speed of sound. But we're not too worried about that. That's it. Great. So, thank you. Have a great homecoming weekend. You're already going, so no questions, I guess.